Hello everyone, my name is Fink. I'm a postdoctoral researcher at the Max Planck Institute for Empirical Aesthetics, but today I'm going to talk to you about some research I did previously when I was still at the University of California, Davis. We know from past research that synchronous motor activity enhances interpersonal cooperation and spontaneous helping in children, as well as cooperation among adults. And in general, that it leads to feelings of connection with others and trust of others. So it's an optimal state to be in, but of course the ability to synchronize with others is limited by our own, motor systems and previous exposure and all these kinds of things. So one question is, given the benefits, is it possible to enhance synchronization abilities of people, especially for those who might not be so good at it? So a previous paper showed that yes, it is possible to enhance synchrony by using an adaptive metronome. So here on the x-axis, they've called it a virtual partner, but basically it was a metronome that was either not adapting at all, that would be 0. So this is their baseline tapping stability. You could think of SD asynchrony as a measure of stability. And they show that when you adapt the metronome by 25 to 50% of the tapper's asynchrony, you can really enhance their tapping performance, their tapping stability, and you can also do the opposite by adapting too much and making it really hard for them to synchronize. And in this paper, they also had people in the scanner and show that different brain networks are involved when you're feeling in sync versus out of sync and needing to exert a lot of cognitive control over the task. So our starting point for this research was, can we do this in groups of people? So we built a new multi-person adaptive metronome system. We replicated that previous single-person experiment using our new system, and we also then now extended it to group context and explored a bit the role of auditory feedback. Our system was built using all open source hardware and software, so Arduino Unos, Adafruit wave shields for playing sound, force sensitive resistors for tapping. All the code was in C++, meaning super low latency. So our system has about less than 1 millisecond lag between you tapping and it getting registered, whereas the previous study used max MSP, and there's about 13 milliseconds latency. We then use Python to communicate between the Arduinos and an experiment control computer, but that wouldn't even be necessary. I mean, you could do it all just locally on the Arduinos. So here's what it looked like. We had 4 Arduinos tied into a central metronome Arduino. Each of the 4 tapping Arduinos had the tap pad. When it taps here, it sets a pin high, which then sends a signal to the metronome. The participants weren't seeing that. It was kind of all under this box. And here's a close-up of one of the tap pads. And here it is in schematic form. The point I want to make here is that the metronome was always through the speaker. At each station, there were headphones and a speaker where participants could either hear the sound of their own tap through headphones or their tap through a speaker. So in the case where everyone's taps are coming through a speaker, it's possible then to hear everyone. And yeah, like I said before, you could be in the other room kind of controlling things through the other computer, which is through the serial port into the metronome Arduino. And eventually all the wiring diagrams for all of this will be made available. So in summary, this is what we're doing. First replicating Fairhurst, then doing the same but with auditory feedback, and then 3 group experiments. We wanted the trials in the group experiments to be a bit longer, so we used only 4 adaptivity conditions rather than the 5 of the initial paper. In the experiment, we told participants to listen for 2 clicks and start tapping with the 3rd click, that they should try to maintain the initial regular tempo of the metronome, and by default that it would click at regular intervals. However, it would adapt based on their performance. We told them to tap in the center of the pad with the index of their dominant hand. Here's what the metronome sounded like, and here's what their tap sound sounded like in the experiments where they could hear themselves, but not always could they hear themselves. What's going on under the hood is that each subsequent click of the metronome is being adjusted by this algorithm. So here I'm talking about the group context, but in the single person context, it's exactly the same, except that we weren't taking this average. So it's the time of the next click is equal to the time of the current click plus an IOI. Always we started with 500 milliseconds, plus this term, which is the asynchrony of the player for the single person case, or the average asynchrony of the whole group for the group case, and asynchrony is the time of their tap minus the time of the metronome, multiplied by this alpha parameter, which is the adaptivity. So Yeah, if you're 100 milliseconds late and we're adapting by 100%, then the next click comes 100 milliseconds late. If we're only adapting by 25%, the next click comes only 25 milliseconds later. After each round of tapping, we asked participants how in the groove they felt, how synchronized with the metronome they felt, and we did tell them the difference here is that being in the groove is this effortless, pleasurable feeling of oneness with the task, whereas synchronization is just objectively how well did you think your taps were aligned with the metronome. We also asked them how much they would like to continue the task, to what degree they felt they had influence over the metronome, and how difficult it was. In the multi-person experiments, we asked how in synchrony with the other players they felt. There were some other surveys we collected, but there's no time in 10 minutes to tell you. So we had a lot of people come into the lab to do this, over hundreds of people, especially to get so many groups of 4. And here are the results. First, the single tapper experiments. The solid line is when participants could hear only themselves. The dashed line is when they could hear when they could hear only the metronome. The dashed line is when they can hear also themselves. So we see in general performance is better when they have auditory feedback, but in both cases that performance is enhanced at 25-50% adaptivity. So again, 0 is the baseline comparison. What you're seeing in the plot is the same as what's over here in numbers, the adaptivity condition and their tapping asynchrony. So we see about like 8 millisecond enhancement when they're hearing themselves, and a bit like 3 to 4 milliseconds when they hear the metronome versus when they hear themselves. But in general, so this is an exact replication of the Fairhurst paper. We see that our system is working as we expect it to, and that hearing yourself improves synchronization. But in general, the adaptivity is useful regardless of the auditory feedback. Here now are the group experiments. The solid line is when they could hear only the metronome. The dashed line is when they could hear only the metronome and themselves. And the dotted line is when they're hearing the metronome and everyone else and themselves. So like hearing all. And this is interesting, yeah, that the best performance is actually when they can hear only themselves and the metronome. So maybe hearing everyone kind of is a bit of interference, but also everyone had the same tap sound. So it could be that if we would change and give each player a unique tap sound, maybe that would somehow be a bit better. That's something to explore in future experiments. But in general, the big takeaway here is, yeah, that this works with groups of people. And here we see the same kind of U-shaped function of the previous experiments. But with the auditory feedback, it seems that groups are able to maintain tapping stability even at these higher levels of adaptivity. So now onto their subjective experience, we find that a lot of those ratings are highly correlated with each other. The group experiments are in parentheses. So we did a factor analysis. We did this individually for each experiment, and we find that the same factor structure really replicates across all 5 experiments, where groove, synchrony, liking all load positively on this factor, and difficulty loads negatively. Influence doesn't really make a difference. So we've termed this factor enjoyment. And now we plot their enjoyment scores by metronome adaptivity. Single tapper experiments on the left, group tapping on the right. We again find this, with the solid line, not much difference in enjoyment at the low levels of adaptivity, but a huge decrease when we get to higher levels of adaptivity. Whereas when people can hear themselves, we see a big increase in enjoyment at the optimally adaptive conditions that's returning to baseline when we become too adaptive. And in the group experiments, yeah, when you can hear yourself, that's at 35, 75, 70%, whereas when you can hear all, it's really only just at 35%, but already decreasing by 70. So yeah, the feedback matters. But in general, this is super interesting because not only can we push around their motor synchrony, also their subjective experience using this multi-person adaptive metronome. So I think I've now said all these things. We've replicated the single person experiments. We show that we can bring people into tighter synchrony than they're capable of without an adaptive metronome, that all these subjective ratings reduce to 1 factor, and that auditory feedback matters. We also see, if we look at musicianship scores on the Gold MSI, that both musicians and non-musicians benefit from this. And there's a lot of other exploratory analyses we did with that, but I want to tell you about some future directions and not get too into that today. So in the future, we could imagine different metronome algorithms, so like taking a weighted average of the players rather than just the average overall, having them tap to different regimes, something more interesting than isochrony, maybe like a clave-son pattern, or using different sonic properties of The experiments of the metronome sound, the attack and duration of that sound are known to influence the perceptual center of the beat. You can imagine giving different players different sounds and exploring different tempi. You could also imagine different rules between players, like assigning certain players leader-follower rules, and investigating that in dyads, triads, and quartets. So there are a lot of possibilities that we're looking forward to, and we hope other people might carry out some of these using our system. And with that, I'd like to thank you for your time and thank our funding agency, and I look forward to your questions.